Please welcome the Senior Vice President of Utility Computing at AWS, Peter DeSantis.
Thank you. Welcome to reInvent 2024. And thank you for joining us for another installment of Monday Night Live, or, as I like to call it, Keynote Eve. We have a great band, good beer, although I do want to apologize. I found out we didn't have any IPA. I will rectify that next year for the IPA lovers. I apologize. That is my fault. All right. Tonight, we're going to do what we normally do, and we're going to dive deep on some of the technical innovations. And like any good Keynote Eve, we might get one present to unwrap, maybe one. We'll see. But we're going to start with the most important thing, which is what we like to do here on Monday Night Live is look at the how. And the how is important, because the how is how we deliver on some of the most important attributes of cloud computing. These are not simply features that you can launch. These are things that you need to design into the services. And that's exactly what we do. These are manifestations of the way we build. And tonight, I thought that it might be fun for me to explain a little bit about why I think AWS is uniquely good at delivering on these capabilities. And in preparing this part of the keynote, I decided to try using an AI assistant. I've been inspired by the way my teams and the teams all across Amazon have been using AI assistants to do things like write code, create creatives, and I thought this would be a fun chance to experiment. So I told my AI assistant how I wanted to start off this presentation and how I might want to visualize it. And I got some ideas. The first idea I got was an iceberg. Because what I wanted to talk about was what was below the surface. But I didn't really like the iceberg analogy. With an iceberg, you only see the small tip of the iceberg, but the only thing below is ice. The second analogy I got was much better. It was a space flight. And the AI assistant said I should explain that while we only see the brief launch, there are large teams of engineers and operators and designers behind the scenes. And that made a little more sense. But it still didn't quite hit the sweet spot of what I was looking for. So after a little more back and forth with my AI assistant, we decided I was going to talk about trees. Now, trees represent the big differentiated technical investments that we discuss each year. Things like our long-term investments in custom silicon, which enable the highest performance and the lowest cost infrastructure options for AWS customers. Also, our investments in AWS custom hypervisors, which enable secure serverless computing. Or our deep investment in database technologies, which allow us to provide differentiated database features and performance. But before we talk about the trees tonight, I want to talk about the roots, the critical structures underneath the trees that support and nourish them. And let's start with the taproot. Now, not all trees have taproots, but the ones that do enjoy unique access to water deep below the surface, allowing them to thrive even when conditions are harsh. And one of the most unique things about AWS and Amazon is how our leaders spend considerable time in the details. And being in these details matter, because when you're in these details, you know what's really happening with your customers and your service. And that empowers you to make fast decisions, possibly fixing or preventing issues before they even happen. Now, this happens other places, but often that information has to percolate up many layers of the organization. And this never happens quickly enough. Just think about how much fun it is to tell your boss when something's not going well. It's no one's favorite thing to do, and it usually doesn't happen nearly quickly enough. Now, it's easy to say that you want to stay in the details. The hard part is building the mechanisms that you need to make sure you do it at scale. And that's exactly what we do. A great example of this is every Wednesday, we run an AWS-wide operations meeting where all of our teams get together and discuss issues, share learnings, and learn from each other. And this is a critical mechanism to keep our leaders, including me, in the details. Now, being in the details also helps us in other ways. And one of those ways is making it easier to make the hard long-term decisions that we have to make. A good example here was the decision that we made to start investing in custom silicon. Now today, this seems like an obvious decision. But 12 years ago, it was anything but clear. Being in the details, we knew that we would never be able to achieve the performance and security that we needed for AWS without something like Nitro. And so we made the decision to join with the Annapurna team on what's turned out to be one of the most important technical enablers of our business. If it wasn't for our deep understanding of the challenges, we could have easily decided to wait. But fortunately, we didn't wait. And the AWS story is entirely different because of that decision. Now tonight, we're going to share the next chapter in that story. Now, while I love the analogy of the taproot, deep roots are not what supports the most massive trees. Instead, trees rely on horizontal root structures. A fascinating example of these horizontal root structures are the buttress root systems of the Amazon rainforest. These above-ground root systems support some of the world's largest trees, growing in unstable soil systems. And buttress roots can span hundreds of feet from the base of a tree, and they can actually interlock with nearby trees to create a foundation to support these massive giants of the rainforest. And that brings me to another unique characteristic of AWS, our ability to innovate across the entire stack, from data center power to networking to chips to hypervisors to database internals to high-level software. Few, if any, companies are invested so deeply across so many critical components. This week, we'll show you how that breadth of innovation enables us to create very unique and differentiated capabilities for you, our customers. But these buttress root systems are only one of the amazing ways that trees are interconnected. Perhaps the most amazing and unexpected is the wood wide web. We often think of mushrooms as these fungi that grow out of the ground. But mushrooms are actually the fruit of the fungi that grows below the ground, a massive organism that actually lives in the roots of trees. And trees have a symbiotic relationship with this fungus. And they use it to communicate and share information and resources with one another. And this makes the forest stronger than any individual tree. And this brings me to what I think is the most important and unique thing about AWS, the culture that underpins everything we do. Now, when I joined AWS, or Amazon, in 1998 as a young engineer, I was surprised by how much focus our leadership put on building culture at such an early point in the evolution of our company. Our senior leaders took the time to build mechanisms that would enable us to scale to the company that we are today. We took the time to write down our leadership principles. We took the time to build a bar raiser program to keep ourselves honest on holding the high bar for the people that we wanted to hire. We built mechanisms like the weekly operations meeting that I showed you earlier to make sure that we were not relying on good intentions as we scaled. Now, in hindsight, it's easy to see how wrong I was about the urgency of these investments. The thing about culture is you either have it or you don't. And if you don't, good luck getting it. And our culture is unique, and it helps us scale while maintaining a steadfast focus on security, operational performance, cost, and innovation. And in the spirit of scaling innovation, I'm going to try something new this evening. I thought it would be interesting for you to hear about some of the innovations we talk about tonight from other leaders of AWS driving some of these innovations. So please join me in welcoming to the stage our VP and longtime leader of AWS Compute and Networking, Dave Brown.
Well, thanks, Peter. It's great to be here. My AWS journey began nearly 18 years ago as part of a small 14-person team in Cape Town, South Africa. And we were building what would become EC2, the Elastic Compute Cloud. And our mission was ambitious, architecting the foundational orchestration layer that would ultimately go on to power the cloud. And what we did not know then was that this was just the beginning of a much bigger transformation in computing. And since that time, we've been on a journey reinventing every aspect of our infrastructure and delivering maximum resilience, performance, and efficiency for our customers. And a significant part of that journey has been rooted in our custom silicon development. When we first introduced Graviton in 2018, it wasn't about having the fastest chip. It was more about sending a signal to the market, giving developers real hardware to play with, and igniting industry collaboration around ARM in the data center. We then set our sights on something much more ambitious. Our first purpose-built processor designed entirely from the ground up. With Graviton 2, we focused specifically on scaled-out workloads because that's what our customers saw and what they were pushing the boundaries with at the time. Web servers and containerized microservices, caching fleets, distributed data analytics. And this was the moment that ARM truly arrived in the data center. And with Graviton 3, we expanded our reach. While we delivered substantial performance gains across the board, we zeroed in on specialized workloads that demanded extraordinary compute power. And the results were dramatic. From machine learning inference to scientific modeling, video transcoding, and cryptographic operations, we more than doubled the performance for many compute-intensive workloads. And today, Graviton 4 represents the culmination of everything we've learned about building processors in the cloud. It's our most powerful chip yet. And with multi-socket support and 3 times our original vCPU count, it's a game changer for the most demanding enterprise workloads like large databases and complex analytics. And with each generation of Graviton, customers have been able to simply switch to the latest instance types and immediately have seen better performance. Now let's take a look at how we've optimized Graviton's performance for real-world workloads. A modern CPU is like a sophisticated assembly pipeline, with a front end that fetches and decodes instructions and a back end that executes them. When we evaluate performance, we look at how different workloads stress the microarchitecture of the CPU. Now, is the workload sensitive to front-end stalls, which are influenced by factors like the number of branches or branch targets or instructions? Or maybe the workload is sensitive to performance is impacted by back-end stalls, which is influenced by data in the L1 and L2 and L3 caches, and the instruction window size. Now, traditionally, micro benchmarks have been used to stress the processor's architecture. Take this benchmark, for example. It's hammering the L3 cache, creating a huge number of back-end stalls. In engineering speak, this means the CPU pipeline is sitting there, twiddling its thumbs, waiting for data that keeps getting kicked out of the L3 cache. And for years, the industry has been obsessed over optimizing benchmarks exactly like this one. But this is like training for a marathon by running a 100-meter sprint. Sure, you're running in both cases, but you're fundamentally training for different challenges. And real-world workloads don't behave anything like these neat and tidy benchmarks. They're messy, unpredictable, and honestly, they're far more interesting. Let's take a look at what happens when we put this micro benchmark next to real-world applications like Cassandra, Groovy, and Nginx, workloads that our customers are running every single day. Now, while the micro benchmark was all about the back-end stalls, in these real-world workloads, they are bottlenecked on an entirely separate set of factors. The branch predictor is missing more. There are lots of instruction misses out of the L1 and L2 cache. There's TLB messes. And unlike the micro benchmarks, the front end is causing all the stalling. And this sums up to the front end stalls being higher, not the back end stalls like we saw with the micro benchmarks. And that's why at AWS, we obsess over real-world workload performance. When we're designing our processes, we're not trying to win a benchmarking competition. We're excelling at running your actual applications. And these are the results of being laser-focused on the real workload. With Graviton 3, traditional benchmarks showed 30% improvement over Graviton 2. Not bad, right? But wait for it. When we tested Nginx, we saw a stunning 60% performance improvement. Why? Because we dramatically reduced branch mispredictions, something that those standard benchmarks barely cared about. And with Graviton 4, we've seen the same pattern play out again. The micro benchmarks suggest a 25% improvement, but real-world MySQL workloads, well, they're seeing 40% better performance. Think about what that means for customers running large databases. And that's why customers love Graviton 4. These aren't just numbers on a slide. These are real customers seeing real improvements, which go on to benefit their customers. Now, at AWS, we're not just talking about Graviton's benefits. We're experiencing it firsthand by migrating our services, and we're seeing remarkable performance improvements. Services like Aurora and DynamoDB and Redshift and more, they're all seeing significant benefits by running on Graviton. And on Amazon Prime Day, one of the largest shopping events in the world, we had over 250,000 Graviton CPUs powering the operation. And recently, we've reached a significant milestone. Over the last 2 years, more than 50% of all new CPU capacity landed in our data centers was on AWS Graviton. Think about that. That's more Graviton processors than all the other processor types combined. But Graviton wasn't the first place that we innovated at the silicon level. Early on, we knew that if we were going to deliver world-class performance and security for the ever-growing number of EC2 instances, we would need to innovate down the entire stack. And that story is the AWS Nitro system. The AWS Nitro system is a complete reimagining of the server architecture and has fundamentally changed and transformed how we build and secure the cloud. With Nitro, we removed the traditional virtualization tax that other cloud providers still deal with today. We also have the agility that we get from Nitro's architecture that allows us to turn virtually any computer into an EC2 instance. You want to run an Apple Mac in the cloud? Well, Nitro did that. You need direct access to the underlying hardware on a bare metal EC2 instance? Nitro handles that as well. But let's focus on where this journey began. Security. Nitro didn't just improve security, it revolutionized our entire approach to hardware supply chain integrity. Now, security in the cloud demands absolute certainty. At AWS, we need to know that every piece of hardware is running the software we expect and the way that we expect it. This goes beyond simply updating software and firmware across the fleet. You need cryptographic proof, what we call attestation, that tells us what's running on every single system. And at our scale, that's an enormous challenge. Think about it. We're proving the integrity of millions of components across our global infrastructure in real time. Let's think about the processor boot sequence as a series of carefully orchestrated steps. It all begins with the read-only memory, or ROM, which activates most of the fundamental parts of the chip. And from there, the processor loads the next layer of firmware, then the bootloader, which hands off to the operating system, and finally to your applications. But here's the critical insight. Each of these steps represents a potential weakness, a place where unauthorized code could potentially run. And even more fundamentally, this entire chain depends on a root of trust. So the real question then becomes, how do you validate that very first link. And to do that, we have to go all the way back to the beginning, the manufacturing floor. A service journey is long, from the initial manufacturing and then the assembly through our shipping lanes and to our data centers, and finally to installation. At each step, we must have confidence that nothing has been compromised. This isn't about finding vulnerabilities after the fact. It's about creating an unbroken chain of custody and verification from the moment that the components are manufactured until they're actually running real customer workloads. So let's dive into the boot process of one of our Graviton 4-based workloads. The foundation of our hardware security and that root of trust lies within the Nitro chip itself. During the manufacturing of each Nitro chip, a unique secret is generated and stored within the chip. You can think of that as the chip's unique fingerprint, and one that never leaves the silicon. And this secret becomes the basis for a public-private key pair. The private key remains permanently locked within the chip, while the public key becomes part of our secure manufacturing record. And this is where our chain of custody begins. The private key in the Nitro chip becomes the anchor for a measured boot process. At each stage of the boot, we create and sign a new private key, destroying the previous private key. This is like passing a secure baton. Each handoff must be perfect, or the race stops. And this chain of signatures lets us verify everything, from the chip's production quality to its firmware version to its identity. A system has limited access to the rest of AWS until it passes this complete attestation process, and any failure means immediate isolation and investigation. But with Graviton, we've pushed the security boundary here even further. So building on Nitro's secure foundation, we've extended attestation to the Graviton 4 processor itself. And this actually creates an interlocking web of trust between the crucial system components. So when two Graviton 4 processors need to work together, they first cryptographically verify each other's identity and establish an encrypted communication. And the same happens between Graviton 4 and Nitro, with the key exchange being tied to the host's identity and that private key. Think about what this means. Every critical connection in the system, from CPU to CPU communication to PCIe traffic, is protected by hardware-based security that starts at manufacturing. With Nitro and Graviton 4 working in concert, we've created a continuous attestation system. This isn't just an incremental improvement in security. The combinations of Nitro's hardware-based security and Graviton 4's enhanced capabilities creates one of our most secure computing offerings yet. For you, this means your workloads run on hardware that's cryptographically verified from the moment of manufacturing through every second of operation. Security that's simply impossible to achieve with traditional servers and data centers. But what other challenges can we solve with Nitro? Well, to understand that, we'll need to look at the dynamics of storage. The evolution of hard drive capacity has been relentless. Every few years, drive manufacturers have found new ways to put more data onto their platters. And if we look back at the early days of AWS around 2006, we were using drives that were measured in hundreds of gigabytes. Today, we're deploying drives that are 20 terabytes and larger. Now, at the same time, the cost per terabyte of storage has dropped dramatically over the past several decades due to innovations in the design and manufacturing process and the materials. And so, to ensure that we're always operating our storage systems as efficiently as possible, we need to make sure that we're always ready to take the next drive size and the next storage innovation. Now, to better understand the complexities that this creates, let's take a closer look at the design of a typical storage system. When we think about storage services like S3 and EBS, they're made up of three critical components. First, you have your front-end fleet. These are web servers that handle the API traffic, authentication requests, and manage the customer interface. And behind that sits what we call the index or mapping service. You can think of this as the brains of the operation. It keeps track of every piece of data and exactly where it's stored. When a customer wants to read their data, this service tells us exactly where to go and find it. And finally, we have the storage media layer. This is where your actual data lives. So let's zoom in on that storage server. Traditionally, our storage servers have been built with what we call a head node architecture. The head node itself is essentially just a standard compute server. It has a CPU, memory, networking capabilities, and it's running specialized software that manages all the aspects of data storage, including critical functions like data durability and drive health monitoring and coordinating all the I/O operations. And connected to this head node, we have what we affectionately call a JBOD. That just stands for just a bunch of disks. And that's literally what it is, a chassis filled with hard drives, all wired directly to the head node through SATA and PCIe connections. But here's the thing. With this design, the ratio between compute and storage is fixed at design time. Once we build and deploy these servers, we're locked into the specific ratios of CPU, memory, and storage capacity. Now, as drive capacities have grown dramatically over the years, this fixed ratio has become more and more challenging to manage effectively. So the net result is that we've been on a journey, increasing the capacity of our storage systems by increasing both the drive size and the number of drives. And we started with relatively modest configurations, maybe 12 or 24 drives in a server. And as drive technology improved, we got better at managing larger drive pools. We kept pushing these numbers up. 36 drives per host, and then 72, always trying to find the sweet spot between density and manageability. And then we created Barge. Barge was our most ambitious storage density engineering project yet. A massive storage server containing 288 hard drives in a single host. Just think about that number for a moment, 288 drives. With today's 20 terabyte drives, that's almost 6 petabytes of raw storage in a single server. That's more storage than some of our data centers had in the early days of AWS. Now, this was our attempt to really push the boundaries of what was possible with storage density. And while it was an impressive engineering achievement, it taught us some crucial lessons about the limits of density. The first lesson Barge taught us was about the physical constraints, and these were literally heavy constraints. Each Barge rack weighed in at an unbelievable 4,500 pounds. That's more than 2 tons. And this created some real challenges for us in our data centers. We had to reinforce the floors, carefully plan the deployment locations, and use specialized equipment just to move these things around. Now, packing 288 spinning drives together not only increases the weight, it also creates what I like to call a vibration orchestra. Housing drives together isn't typically a big deal. But when you have 288 of them spinning at 7,200 RPM, the vibration effects can become significant enough to actually impact the performance and reliability of the drives. And then there's the software complexity. Managing 288 drives from a single host pushed our software systems to their limits. Think about all the different failure modes that you need to handle, the complexity of data placement algorithms, and the challenge of maintaining consistent performance across such large drive pools. But perhaps the most critical lesson was about blast radius. When a Barge server failed, and servers do fail, the impact was massive. You're suddenly dealing with the potential unavailability of 6 petabytes of storage. And even with redundancy, the recovery process for that much data takes a significant amount of time and network bandwidth. And so we knew that we had to say goodbye to Barge. So with those lessons learned, we had to take a step back. How could we reduce the operational complexity while increasing the agility of our storage infrastructure, while still delivering high performance for our customers? And for that, we turned to our storage services for insight. So storage services like S3 and EBS and EFS were all built on our standard storage server architecture, but they had some unique requirements. Some services needed more memory. Some needed less compute. But within the storage layer itself, the functions were identical. So was it the tight coupling between compute and storage that was limiting us? The concept of disaggregation, separating the compute and the storage, started looking very, very attractive. If we could find a way to keep the direct access and the performance that our services needed, while allowing independent scaling of compute and storage, we might be able to get the best of both worlds. And this is where we started thinking about leveraging something that we already had in our toolkit, Nitro. So instead of connecting those drives to the head node, we're disaggregating storage by embedding Nitro cards directly into those JBOD enclosures. Think of these Nitro cards as giving our drives their own intelligence and network connectivity. Each drive is a securely virtualized, isolated network endpoint. And what's really powerful about this approach is we're preserving the direct low-level access that our drives and our storage services needed, while we're completely breaking free of the physical constraints that we had before. And Nitro handles all of the networking complexities, the encryption, and the security. And because Nitro is designed for high performance and low latency, we're delivering all of the drive's native performance, even when we access it over the network. And this is what it actually looks like in our data centers. At first glance, you might think this looks like a standard JBOD chassis, but there are some key differences. Those Nitro cards we talked about are actually embedded here along with the drives. And the beauty of this design is its simplicity. When you look inside a rack of these, you'll see something that looks more like a network switch than a traditional storage server. And this also made maintenance simpler. Thanks to our disaggregated storage architecture, any failed drive can be quickly removed from service and replaced by another healthy drive just with a few API calls. And our hot swappable drive containers allows our data center technicians to easily service these units without impacting service availability. So drive failures are no longer a concern, but what about those head nodes? Well, this is where things get really, really interesting. In the traditional architecture, a head node failure was a major event. You lose access to dozens or hundreds of drives until you could go and repair that server or replace the server. Remember our barge example? A single server failure impacted 288 drives. Well, with disaggregated storage, a head node failure becomes almost trivial. Since the drives are addressed independently on the network, we can simply launch a new compute instance and reattach all the drives. And it's the same process we use for the standard recovery of an EC2 instance, and it typically happens in a few minutes. No data movements required, no complex rebuild process, just reattach and resume operations. And these failure scenarios highlight something crucial. We've dramatically reduced our blast radius while actually improving recovery speed. And this is just the beginning of what's possible when we decouple compute from storage. Another powerful benefit of disaggregated storage is the ability to scale compute and storage independently. In S3, when we land new storage capacity, there's typically a period of heavy compute load as we hydrate and rebalance data across the new drives. And now we can temporarily scale up and scale out compute resources just for this initial period, and then scale back down for normal operations. And this kind of flexibility, it helps us to run more efficiently and ultimately deliver better value for our customers. But with disaggregated storage, we've successfully broken free from those fixed ratios that constrained our storage architecture for many years. By separating compute and storage, we can scale each component independently while maintaining high performance, just like you'd expect in a cloud environment. We've dramatically reduced our blast radius. Now failures can be constrained, recoveries are faster, and our services are more resilient than ever before. And we're seeing real operational benefits from increased agility. Our servers can right-size their compute resources based on their actual needs, not the hardware constraints. And maintenance is simpler, capacity planning is more flexible, and we can innovate faster. But perhaps the most important, this architecture sets us up for the future. As drive capacities continue to grow, disaggregated storage gives us the flexibility to adapt and evolve our infrastructure. What started as a solution to our storage density challenges has become something much more fundamental. A new primitive that helps us build more efficient, more reliable storage services for you, our customers. And with that, I'll hand it back to Peter.
All right. Well, that was awesome. Dave gave you a great peek at some of the innovations on AWS Compute. Now, I want to spend a few minutes talking about an entirely different kind of workload. artificial intelligence. Actually, it's two workloads. There's AI model training and AI inference. And one of the really cool things about AI workloads is that they present a new opportunity for our teams to invent in entirely different ways. We will look at some of those innovations here tonight, like pushing ourselves to build the highest performing chips and interconnect them with novel technologies. But we're also going to look at how we're applying the innovations that we've been driving over the last decade to this new domain, bringing the performance, reliability, and low cost of AWS to AI workloads. Now, we talk a lot about scale-out workloads, like web services, big data applications, and distributed systems. Scale-out workloads run very efficiently when you add additional resources to the system. And we've invested deeply to create infrastructure that's optimized for these workloads. In fact, Dave just told you about some of these innovations earlier. But AI workloads are not scale-out workloads. They're scale-up workloads. And let me show you why that is. One of the things driving the emergence of AI capabilities is that models are getting bigger, much bigger. When I talked about this last in 2022, we were excited about models with billions of parameters. Last year, we were excited about hundreds of billions. And soon, frontier models are likely to have trillions of parameters. Why are we seeing this growth? Well, in 2020, researchers published a groundbreaking paper which is called the scaling laws. And it hypothesized that model capabilities improve as you scale up certain things, namely the number of parameters, the data set size, and the amount of compute. And since then, we've seen a push to build bigger and more compute-intensive models. And these models have indeed gotten more capable. You've experienced this in your day-to-day lives. Now, if you look carefully at these graphs, you'll see that something pretty interesting. These are log-log graphs, meaning that the graphs have logarithmic x-axes and y-axes. And straight lines on log-log graphs can be misleading. Let's take a closer look at the compute graph. Now, we're accustomed to linear graphs, where every time you add an x, you get a y. It's a linear relationship. But in a log-log graph, straight lines represent multiplicative relationships, such as if we quadruple x, we can double y. And what we see in these scaling graphs is mind-boggling. In order to halve the loss, the measure on the y-axis, we need to use 1 million times more compute. 1 million times. Now, a model that's 50% better on this y-axis measurement is actually going to be way smarter on a bunch of other benchmarks. But this relationship between compute and model loss explains why the industry is investing tens of billions of dollars in building better AI infrastructure. But what does better AI infrastructure mean? To understand that, let's look at how large AI models are trained. At their core, modern generative AI applications are prediction engines. You prompt them with a set of tokens, which are basically parts of words, and they predict the next token sequentially, one at a time. And from this really basic skill, predicting the next token, some pretty amazing properties emerge, like reasoning, problem solving. To build such a predictive model, you train a model on trillions of tokens of data until you've found a set of model weights that minimizes prediction error across your training data. And this process of training on all those tokens requires massive amounts of compute. To train the largest models on a single server, even the largest single server, would take centuries or maybe millennia. So of course, we do need to parallelize. The obvious place to start is by splitting up the training data, and this seems straightforward enough. If you take something that takes 1,000 years on one server and you run it on 1,000 servers, it should take a year. And this would be true if the workload was a scale-out workload. But alas, it's not quite that simple. The process I just described, splitting up the data, is called data parallelism. And like lots of good things in life, data parallelism comes with some fine print. If you take the simple divide and conquer approach that I described, you'd really be building a bunch of independent models and then trying to combine them at the end. And that simply doesn't work. Instead, when employing data parallelism, you need all the servers to share and combine their model weights continually, essentially allowing the massive cluster of servers to build one shared version of the model. And this is where something called the global batch size actually comes into play. Global batch size is the largest set of data that can be worked through before you need to combine the results from all your servers. And this global batch size is a real tiny fraction of your overall training data. So here's how data parallelism really works. You grab a chunk of data, not bigger than that global batch size, and next you divide the chunk into a bunch of equal parts and farm it out to all your servers. Then each server trains on their assigned bit of data, and when it completes, it combines its results with everybody else in the cluster. And when everybody's combined the results, then everybody can move on to the next batch of data. So in practice, this limitation, this global batch size limit, means that you can really only scale out a training cluster to a few thousand servers at most. If you go much further than this, each server actually gets such a small amount of data that it spends more time coordinating its results than it does on actually processing the data. So if you keep adding servers, you don't get faster, you just add cost. So understanding this about data parallelism and the limits of this highlights two fundamental pillars of AI infrastructure. First, because we have this scale-out limitation from the global batch size, our path to building larger models is building more powerful servers. This is the scale-up part of the infrastructure challenge. Second, despite the limitations of scale-out in building AI models, we still get a lot of value from building these very large clusters. And to do that well, we need to take advantage of the scale-out tools that we've been building for many years. Things like efficient data centers, fast scaling, and great networking. So let's start by looking at the first part of this, the scale-up challenge. What does it mean to build the most powerful server? It means you want a coherent computing system that has as much compute and high-speed memory packed into the smallest space possible. Now, why does it matter if it's in the smallest space possible? Because getting all this compute and memory close together means you can wire everything together using massive amounts of high bandwidth, low latency connectivity. Now, the latency part's probably pretty intuitive, but the closer things are together, you can also get more throughput. And the reason for that is if you have things closer together, you can use shorter wires to transmit data between them, which means you can pack more wires. It also means you have lower latency, and you can use more efficient protocols to exchange data. So this seems simple enough, but it's a very interesting challenge. Last year, we announced Trainium 2, our next generation Trainium chip. And tonight, I'm going to walk you through how we're using Trainium 2 to build our most powerful AI server ever. Now, let's start with the smallest part of the system, the Trainium 2 chip. I'll point out some of the engineering limits that we're going to hit along the way as we try to take this chip and build the largest AI server. Now, chips are manufactured on silicon wafers with an extremely impressive fabrication technology. And these processes are improving all the time. So if you want to get the most compute and memory on a system, a great place to start is building the biggest chip with the most advanced packaging, or the most advanced fabrication technology. And that's exactly what we did with Trainium 2. But here's where we actually encounter our first engineering limit. The chip fabrication process actually has a maximum size that you can produce a chip. And it comes from the lens that's used to etch the silicon wafer. It's called the reticle, and it limits the maximum chip size to around 800 square millimeters, or 1.25 square inches. Now, you're probably thinking the thing in my hand looks a lot bigger than 1.25 square inches. And that's because the thing I'm holding in my hand isn't the chip, it's the package. When most of us think of computer chips, we think of the thing that sits in the middle of the motherboard, under the heatsink. But that's actually the package. The chip's inside the package. And a few years ago, the package was a pretty simple thing. It was basically a way of enclosing a single chip and attaching it to the motherboard. The package enabled us to move from the really small world of the silicon chip to the larger wire traces that connects everything together on the motherboard. But today, the package is much more advanced. You can think of advanced packaging as connecting several chips inside a single package using a special device called an interposer. An interposer is actually a small chip of itself, and it acts as a tiny motherboard that offers the ability to interconnect chips with about 10 times the amount of bandwidth that you can get on a normal PCB-based motherboard. Now, we've been using advanced packaging techniques in the last couple generations of our Graviton processors. Here you see Graviton 3 and Graviton 4. And you can see both chips, or both packages have multiple chips, or chiplets, inside the package. The Graviton 4 package actually has 7 chiplets. The big chip in the middle are the compute cores. And those smaller chips around the periphery do things like allow the chip to access memory and other parts of the system bus. Now, by separating out the compute cores, we were able to cost-effectively increase the number of cores on our Graviton 4 processor by 50%. Now, this approach has been super helpful with Graviton, but it's table stakes when building a great AI server. Here is the Trainium 2 package, which is what I was holding in my hand. And you can see we have 2 Trainium chips side by side in the middle of that package. Each Trainium 2 chip is sitting beside 2 other chips. These chips are HBMs, or high bandwidth memory modules. HBMs are specialized modules that contain stacks of memory chips. And by stacking the chips, you can pack more memory into the same area. And this is possible because memory chips actually use less power and put off less heat. OK, so if you look at this package, that's a lot of compute and memory. But you might be wondering, why can't we make the package even bigger? Just keep going. And this is where we run into our second constraint. And to understand that, let's have a much closer look. Today, packages are actually limited to about 3 times bigger than the maximum chip size, which is about what you see here if you consider those 2 chips and the HBMs. Now, in this illustration, we took a couple of the HBMs off to give you a peek at the interposer underneath. You can see all the little tiny bumps that are used to connect the chip to the interposer. But there's a better angle to see this. This is a really cool image that the Annapurna team created for me. They took a cross-section of the chip by carefully slicing along that purple line. And then they used a microscope to blow up that image from the side. And you can see some really interesting things. On the top left, you see the Trainium 2 compute chip. And beside it, you see the HBM module. And one very cool thing is you can actually see the layers of the HBM module. And both of them are sitting on a thin, continuous wafer. This is the interposer that interconnects the chips. And the other thing you can see here are the little tiny connections that attach the chip to the interconnector. And you can see those are really tiny little dots. Those electrical connections between the chip and the top of the interposer are insanely small. Each one is about 100 microns. That's smaller than the finest grain of salt that you've ever seen. And all these connections need to stay in place in order for that chip to stay connected. And that's why we have a limit on the size of the package, because the package has to stay stable enough to keep all those connections attached. And don't let these tiny dimensions mislead you, because these chips have a large amount of power and heat moving around. If one of those Trainium chips can do enough calculations that it would do what a human could do in millions of years in a single second. And to do that work, these chips require the delivery of a ton of power. Now, by moving all that power at low voltages, we need to use big wires. Now, big is, of course, a relative term, but you can see the wires here at the bottom of the package. Chips folks would call these power vias. And the reason we need to use big wires is to avoid something called voltage drop. A semiconductor uses the presence or absence of tiny electrical charges to store and process information. So when chips encounter voltage drops, or sags, they typically need to wait until the power delivery system adjusts. And waiting is not something you want to do with a chip. While a chip needs low voltage power, it's more efficient to deliver power at higher voltages. So data centers are actually deliver power at multiple voltages. It's progressively stepped down as it gets closer and closer to the chips. And the final step happens right before the power enters the package. You can see how this is typically done by looking at our Trainium 1 motherboard. The final voltage step down is done via voltage regulators positioned as close to the package as possible. Here, I'm highlighting them on the board. Now, to reduce voltage drop and optimize Trainium 2, our Trainium 2 team worked to bring these voltage regulators even closer to the chip. Here we see the Trainium 2 board, and you'll see no sign of those voltage regulators on the top of the board. Instead, the voltage regulators are actually under the perimeter of the package. And doing this is quite challenging because the voltage generators generate heat, and so you have to do some novel engineering. But by moving those voltage regulators closer to the chip, we actually can use shorter wires. And shorter wires means less voltage drop. Here's a view of Trainium 1. And you can see how it responds when load is increased. This is what happens when you start doing a large amount of computing. And you can see when load spikes, voltage sags significantly. And while this is brief, that voltage sag means the chip is not computing optimally. And extreme variability like this can actually be hard on the chip, potentially reducing its useful life. Now here's a look at the same load being applied on Trainium 2. Notice you have no pronounced voltage drop. And that's because of those shorter wires. And that means no throttling of the chip. And it means better performance. OK, enough about the chip. Let's look at the server. This is a rack with two Trainium 2 servers, one on the top and one on the bottom. They're big servers. Each Trainium 2 server is made up of 8 trays of accelerators. And each tray contains 2 Trainium 2 accelerator boards, each with its own dedicated Nitro cards. And just like GPUs on NVIDIA-based systems, Trainium servers are accelerators. They're designed to do the math and operations needed to build AI models. However, they don't support the normal instructions that you need to run an operating system or a program. For that, you need a head node. And this is actually the engineering limit to our server. The number of Trainium accelerators we can put in a server is actually limited by the ability of the head node to efficiently manage and feed those nodes. So adding additional accelerators beyond what we've done would actually just add cost without adding additional performance. Not what we're looking to do. Finally, you need a switch to connect all the accelerators and the head node to the network. So how powerful is a Trainium 2 server? Trainium 2 server is the most powerful AWS AI server, providing 20 petaflops of computing capacity. That's 7 times more than Trainium 1 and 25% more than our current largest AI server. The Trainium 2 server also has 1.5 terabytes of high-speed HBM memory. That's 2.5 times more than our current largest AI server. Now that's a scale-up server. But having the most powerful AI server only matters if you can get it into customers' hands quickly. A few years ago, when a new chip or server would come onto the scene, you'd see an adoption curve that looks something like this. During the early months of a new server's life, some early adopters might adopt it, usually the largest databases and the most demanding workloads. And while those early adopters were moving their new workloads to the hardware, a lot of the early life manufacturing challenges could be worked through. But that's not how things work with AI. Because of the value of more powerful servers for building better models, customers want access to the best AI infrastructure, and they want it on day one. Anticipating that unprecedented ramp, we innovated here as well. Let's have another look at that Trainium 2 tray that we looked at a moment ago. Now, what's interesting here is what you don't see, and that's a lot of cables. And that's because the team went to great lengths to reduce the number of cables. Instead of cables, all these components are interconnected via wire traces on the motherboards below. Why did they do that? Because every cable connection is a chance for a manufacturing defect. And manufacturing defects slow you down. In fact, One of the coolest things about the Trainium 2 server is it's been designed specifically to enable automated manufacturing and assembly. This high level of automation enables us to scale quickly from day one. So, Trainium 2 is not only our most powerful AI server, it's also specifically designed to scale up faster than any other AI server that we've ever had. But that's not the whole story. A powerful AI server is more than just raw compute and memory packed into a small space. It's a specialized tool for optimizing AI workloads. And that's where the architecture of Trainium 2 comes into play. The first thing to understand about Trainium is that it uses a completely different architecture than a traditional CPU or a GPU, something called a systolic array. And let me show you quickly how it's different. Here we've illustrated a few standard CPU cores executing instructions. While there are different types of CPUs, they all share some common characteristics. First, each CPU core is a fully independent processor. That's why you can run multiple processes concurrently on modern CPUs. And the other thing to notice here is that every CPU core does a small amount of work before returning to memory to read or write data. This makes the CPUs very versatile, but it also means that performance is ultimately gated by memory bandwidth. Finally, while core counts of CPUs have increased a lot over recent years, the largest CPU today may have a few hundred cores at most. The GPU is an entirely different animal. Modern GPUs have hundreds or thousands of computing cores, and they're organized into parallel processing units. And GPUs can pack way more cores onto the same space by having multiple cores execute exactly the same operation on different data. That means each GPU core is not fully independent. It's actually tied to other cores. But it also means that each GPU core can be built with fewer transistors than a fully independent core on a CPU. The GPU architecture has vastly accelerated a number of workloads, starting with graphics, but most notably AI. The GPU is undeniably a transformative hardware architecture. But we chose a different approach. A systolic array architecture is a unique hardware architecture because it allows you to create long, interconnected computing pipelines. With a CPU or a GPU, each compute instruction needs to read memory, does its work, and then it writes back memory. With a systolic array, we can avoid memory access and between computational steps by directly handing off results from one processing unit to the next processing unit. This reduces memory bandwidth pressure, and it allows us to optimize our computing resources. And with Trainium, we actually designed the systolic array for AI workloads. So we don't have a linear chain of processing units like illustrated before, but we have something that looks more like this. Our layout is specifically designed to accommodate the common matrix or tensor operations that underlie AI code. And this architecture gives Trainium an advantage over traditional hardware architectures in making optimal use of the memory and bandwidth available at the AI server, helping us get the most out of the compute and memory that we worked so hard to pack into that Trainium 2 server. Another decision that we made with Trainium is to give you direct access to the hardware, so you can optimize your application's performance. The Neuron Kernel Interface, or NIKI, is a new language that enables you to develop and deploy code that takes full advantage of the underlying Trainium hardware, enabling you to experiment with new ways to more cost-effectively build AI applications. And we're excited to let a lot more people experiment with Trainium. So last month, we announced the Built on Trainium program, which provides access to Trainium hardware to researchers to develop new technologies. Researchers from universities like UC Berkeley, Carnegie Mellon, UT Austin, and Oxford are excited to use Trainium and its novel hardware capabilities to conduct novel research in AI. And we're excited to partner with these research institutions to innovate on the hardware that will power tomorrow's most demanding AI workloads. Okay, so we built the most powerful AI server with a novel hardware architecture that's optimized for AI workloads. And we're ready to ramp faster than ever before. But what about the most demanding AI workloads, powering the latest frontier models? For them, most powerful is never enough. And that's where Neuronlink comes into the story. Neuronlink is our proprietary Trainium interconnect technology. Neuronlink enables us to combine multiple Trainium 2 servers into one logical server with 2 terabytes per second of bandwidth connecting those servers. And they have 1 microsecond of latency. And unlike a traditional high-speed networking protocol, Neuronlink servers can directly access each other's memory, enabling us to create something special, something we call an ultra server. Now, I've always wanted to bring hardware onto stage, and every year I've been talked out of it. It's going to block the screen. By the way, I'm sorry it blocks the screen. But this year, to show you what an ultra server is, we brought an ultra server onto stage. This is one ultra server, 64 Trainium 2 chips working together to provide 5 times more compute capacity than any current EC2 AI server, and 10 times more memory. Now that's the type of server that you need if you're going to build a trillion parameter AI model. Pretty cool. Now, I'm guessing there's at least one person in this audience who's thinking about building a trillion parameter AI model. But for the rest of you, there's going to be something as well. Let's look at something that everybody's doing a lot of, and that's AI inference. Large model inference is a really interesting and demanding workload in its own right. And actually, it's 2 workloads. The first workload is input encoding, where the prompt and the other model inputs are processed in preparation for token generation. This process is referred to as prefill. And prefill needs a lot of computing resources to convert that input into that data structure that gets handed off to the next process. Once prefill completes, the computed data structure is handed off to a second inference workload, which does token generation. And one of the interesting aspects of token generation is that the model generates each token sequentially, one at a time. And this puts a very different set of demands on the AI infrastructure. Each time a token is generated, the entire model has to be read from memory, but only a small amount of compute is used. And for this reason, token generation puts lots of demand on the memory bus, but only a small amount of compute, almost the exact opposite of the prefill workload. So what do these workload differences mean for you and for AI infrastructure? Let's start with you. A short time ago, lots of workloads, like chatbots, mostly cared about prefill performance. And that's because when prefill's happening, the user's typically waiting and staring at a screen or a spinning wheel. But once tokens start being generated, you just needed to generate them faster than the human can read. And that's not very fast. But increasingly, models are being used in agentic workflows. And here, you need the whole response to be generated before you can move on to the next step of your workflow. So now customers care about fast prefill and really fast token generation. And that brings us to the interesting thing that's happening with the demand for AI inference infrastructure. The desire for really fast inference means that AI inference workloads are now looking for the most powerful AI servers as well. Now, the nice thing is these 2 different workloads we talked about are complementary. Prefill needs more compute, token generation needs more memory bandwidth. So running them on the same powerful AI server can help us achieve great performance and efficiency. So we asked ourselves, how can we bring the benefits of Trainium 2 to AWS customers for inference? And I'm excited to announce a new latency-optimized option for Amazon Bedrock, which allows you to have access to our latest AI hardware and other software optimizations to get the best inference performance on a large variety of leading models. Latency-optimized inference is available starting right now in preview for select models. And one of those models is the widely popular Llama. And we're excited that latency-optimized versions of Llama 405B and the smaller Llama 70B model now offer the best performance on AWS of any provider. here's the performance of Llama 405B, the largest and most popular Llama model. We're looking at the total time to process the request and generate the response. So it includes both the pre-fill workflow and the token generation workflow. Lower is better here. And you can see that Bedrock latency optimized offering is a lot lower than other offerings. But what if you use other models? I'm excited to announce that in partnership with Anthropic, we're launching a latency-optimized version of the new and highly popular Claude 3.5 model. Depending on the request, the latency-optimized Haiku 3.5 runs 60% faster than our standard Haiku 3.5, and it provides the fastest inference for Haiku 3.5 anywhere. And like Llama, Haiku 3.5 is taking advantage of Trainium 2 to achieve this performance. But you don't need to just take my word for this. I'm really excited to invite on stage one of the co-authors of the scaling law paper that I mentioned earlier. Please welcome Tom Brown, co-founder and chief compute officer at Anthropic, to share how they're innovating with Trainium and AWS.
Thanks, Peter. At Anthropic, we build trustworthy AI. Each day, millions of people around the world rely on Claude for their work. Claude writes code, edits documents, and uses tools to complete tasks. And I'll be honest, Claude wrote like half of this keynote I'm about to tell you. Now, thanks to our partnership with AWS, businesses large and small can use Claude on the secure cloud that they already trust. I'm going to spend some time digging deeper into how our collaboration works. First, let's talk about Claude 3.5 Haiku that Peter just mentioned. It's one of the newest and fastest models. Despite its small size, it packs a punch, sometimes matching the performance of our largest model, Opus, while costing 15 times less. As Peter mentioned, we work together to build this latency-optimized mode that lets customers run Haiku even faster on Trainium 2. This means, as of today, you can run Haiku 60% faster, no changes needed on your side. You just flip a switch on the API, and your requests get routed to the new Trainium 2 servers. Easy. Now, this speed is great for in-the-loop interactions. So I'm a coder. Imagine autocomplete, where you need to tab complete the suggestions in the short time between keystrokes. A 60% speedup makes a huge difference here. It can be the difference between your completion showing up or not at all. So how did we make it so fast? Well, first off, look at this thing. It's a beast. Look at that machine. And then each of the chips in it has the serious specs that Peter told you, over a petaflop of compute in those systolic arrays. Plenty of memory bandwidth, fast interconnects. It's got great specs. But as every engineer knows, specs aren't enough. To get peak performance, we need to keep those hungry systolic arrays fed all the time. That means sequencing the work so that they're never blocked waiting on their inputs from memory, from the interconnects, from wherever. It's like a game of Tetris, where the tighter you pack it in, the cheaper and faster the model becomes. So how do we solve this Tetris game? Well, Anthropic's performance engineering teams have been working closely with Amazon and Annapurna on this challenge for over a year. We found that the compiler can do a lot, but it's not perfect. And at our scale, it's worth trying to be perfect. A single performance optimization for Anthropic can unlock enough compute to serve 1 million new customers. This means it's worth it to drop down to a lower level, like Nikki, and write kernels as close as we can to the raw hardware. It's like moving from Python to C for the most important parts of a program. And we found that Trainium's design is great for this type of low-level coding. So folks might not know this, but for other AI chips, there's actually no way to know which instructions are running in your kernel. This means you have to guess. It's like playing Tetris with a blindfold. Trainium is the first chip I've seen that can log the timing of every single instruction executed anywhere in the system. Let me show you. Here's an example of a real low-level Trainium kernel that we developed at Anthropic. You can see here exactly when the systolic arrays are running, when they were blocked, plus we see exactly why they were blocked, what they were waiting for. You get to take off the blindfold. This makes writing low-level kernels faster, easier, and in my opinion, way more fun. OK, speaking of fun stuff, I have something to announce. You see, so far we've been focusing on inference, but they don't call it Trainium for nothing. I'm excited to announce that the next generation of Claude will train on Project Rainier, a new Amazon cluster with hundreds of thousands of Trainium 2 chips. So hundreds of thousands of chips means hundreds of dense exaflops, over 5 times more than any cluster we've ever used. So what does Rainier mean for customers? Well, the world has already seen what we've been able to do with our last cluster. Earlier this year, Anthropic shipped Claude 3 Opus, the smartest model in the world. 4 months later, we shipped Claude 3.5 Sonnet, even smarter than Opus at a fifth the cost. Then, in the last month, we've shipped both 3.5 Haiku and an upgraded 3.5 Sonnet that can use computers like a human. Project Rainier will speed up our development even more, powering both our research and our next generation of scaling. This means customers will get more intelligence at a lower price and at faster speeds. Smarter agents that they can trust with bigger and more important projects. With Trainium 2 and Project Rainier, we're not just building faster AI, we're building trustworthy AI that scales. Thank you.
Thank you, Tom. Innovating with Anthropic this past year has been an exciting journey, and we're energized by the possibilities of what's to come. OK, I mentioned earlier that to build the best AI infrastructure, you need to build the most powerful server. That's the scale-up part of the problem. But that's only half the story. If you want to train the largest models, you also need to build the largest clusters, like Project Rainier. And this brings me to the second half of the story, the scale-out story. And this is where AWS's long history of innovating with high-performance scale-out infrastructure really comes in handy. A great example of this scale-out innovation is on building an elastic AI-optimized network. Now, a great AI network shares a lot in common with a great cloud network, although everything gets ratcheted up massively. If this were a Vegas fight, it wouldn't even be a close fight. Sure, a cloud network needs lots of capacity to make sure the network is never in the way of customers. In fact, James Hamilton talked about this on our very first evening keynote. But an AI network needs way more capacity. Recall that each Trainium 2 Ultra server has almost 13 terabits of network bandwidth. And during training, every server needs to talk to every other server at exactly the same time. So the network needs to be massive to make sure that it never slows down those servers. Cloud networks need to scale fast to accommodate growth. We add thousands of servers to our worldwide data centers every day. But as discussed a bit earlier, AI is scaling even faster. When you're spending billions of dollars building AI infrastructure, you want it installed immediately. And cloud networks need to be reliable. They've delivered, providing significantly better availability than can be achieved by even the most sophisticated on-premise networks. Our global data center network has 5 nines of availability. But here, too, AI workloads are more demanding. If an AI network experiences even a transient failure, the training process can be delayed across the entire cluster, leading to idle capacity and longer training times. So how do you build on the innovations of a cloud network to create a great AI network? Here's a picture of our latest generation AI network fabric, something we call the 10P10U network. This is a network fabric that powers our Ultra Server 2 cluster. And we use that network for both Trainium and NVIDIA-based clusters. We call it 10p10u because it enables us to provide tens of petabits of network capacity to thousands of servers with under 10 microseconds of latency. And the 10p10u network is massively parallel and densely interconnected. And a 10p10u network is elastic. We can scale it down to just a few racks, or we can scale it up to clusters that span several physical data center campuses. And what you're looking at here is just a single rack of 10p10u. Now, you might have noticed the switches are a beautiful shade of green. Green's actually my favorite color. I prefer a British racing green, but it's a nice color. So I've never seen green switches in our data center before, so I asked the team, why this shade of green? Well, this shade of green is called greenery, and it was the 2017 Pantone Color of the Year. And apparently, one of our suppliers had some excess paint and offered us a very good deal. And I love this story because it captures our design philosophy. Spend money on the things that matter to customers and save money on the things that don't, like paint. Now, the other thing you probably noticed here is there's a lot of networking cables into this rack. The part of this that isn't green is the network patch panels. To build a dense network fabric like this, you need to interconnect the switches in a very precise pattern. And that's what this patch panel enables. And these patch panels have served us well for many years. But as you can see, things are getting pretty messy with the 10p10u network because the cable complexity has grown significantly. And as discussed, we're installing things even faster. And so this was a prime opportunity for the team to innovate. One of their innovations was developing a proprietary trunk connector. You can think about this as a super cable that combines 16 separate fiber optic cables into a single robust connector. And what makes this game-changing is that all that complex assembly work happens at the factory, not on the data center floor. And this dramatically streamlines the installation process and virtually eliminates the risk of connection errors. Now, while this might sound modest, its impact was significant. Using trunk connectors speeds up our install time on AI racks by 54%. Not to mention making things look way neater. Those green switches really pop now. But the team didn't stop innovating here. Here's another great innovation. They call it the Firefly Optic Plug. And this ingenious low-cost device acts as a miniature signal reflector, allowing us to comprehensively test and verify network connections before the rack arrives on the data center floor. And that means we don't waste any time debugging cabling when our servers arrive. And that matters, because in the world of AI clusters, time is literally money. But it doesn't stop there. The Firefly plug serves double duty as a protective seal, which prevents dust particles from entering the optical connections. And this might sound minor, but even tiny dust particles can significantly degrade the integrity and create network performance problems. So this simple device improves networking performance as well. So with one eloquent solution, we've solved two critical challenges. The illustrative feeding two birds with one stone. And it's innovations like this that helped us make the 10p10u network our fastest scaling network ever. And you can see the number of links we've installed in our different network fabrics on this chart. And the ramp of the 10p10u network is unprecedented, even for us. We've installed over 3 million links in the last 12 months. And that's before we've even started to look at our Trainium 2 ramp. And that brings us to our final challenge, delivering higher network reliability. The biggest source of failure in an AI network is the optical links. Optical links are the miniature laser modules that send and receive optical signals on all these cables we've been looking at. Now, AWS has been designing and operating our own custom optics for many years. And as a result, our operational rigor and our massive scale, we've been able to drive down the failure rate consistently. And this is impressive progress that comes from scale. But no matter how far we drive down these failures, we're never going to be able to eliminate the failures entirely. So we need to look at how we can make the failures less impactful. And every network, switches need data to tell them how to route packets. These are basically maps of the network. And in an AI network, this map might need to consider hundreds of thousands of paths. And every time an optical link fails, the map needs to be updated. So how do we do that quickly and reliably? The simple approach is to centrally manage the map. One brain optimizing the network sounds really appealing. But there's a catch. When your network is massive, central control becomes a bottleneck. Detecting failures is hard, updating switches can be painfully slow, and the central controller is a single point of failure. That's why large networks typically go decentralized, using protocols like BGP and OSPF. Switches share health updates with neighbors, and they collaborate to produce a network map that works for them. And these approaches are robust, but not perfect. In a large network, when links fail, it can take significant time for the network switches to collaborate and find a new optimal map for the network. And in AI networks, that's time you're not doing work. So when faced with two suboptimal choices, you often need to forge a new path. So with our 10p10u network, we decided to build an entirely new network routing protocol. We call this protocol Scalable Intent-Driven Routing, or CIDR. And yes, for the networking people in the room, that might be a pun. CIDR gives you the best of both worlds. An easy way to think about CIDR is you get the central planner doing the work to distill the network into a structure that can be pushed down to all the switches in the network so that they can make quick, autonomous decisions when they see failure. So CIDR gives us central planning's control and optimization with decentralized speed and resilience. And the result? CIDR responds to failures in under 1 second, even on our largest 10p10u networks. That's 10 times faster than the alternate approaches that we use on other network fabrics. And while other networks might still be recalculating routes, the 10p10u network is back to work. All right, we've spoken about a lot this evening. From core innovations Dave spoke about across our investments like Nitro and Graviton and storage, to how we're building our largest, most powerful AI server with Trainium 2, to how AI is benefiting from our years of scale-out cloud innovation. Hopefully, you'll leave here tonight with an understanding of how we're innovating across the entire stack to create truly differentiated offerings for you, our customers. With that, I want to say goodnight, thank you, and enjoy your reInvent.